Good afternoon, everyone. I'm Yu Xinggu, a student from Beijing University of Post and Telecommunications. Now, let me tell you about our paper, Learning to Distill Graph Neural Networks. This presentation is divided into the following four parts. First, I will briefly introduce the background of this paper, then introduce the methods of this paper in detail, and next, I will introduce the experiments we have conducted and the results of the experiments. Finally, I will give a conclusion of our work. Let's begin from the background of our work. Graph is a common data structure that is a collection of nodes and the relationships between those nodes. The power of graphs lies in their focus on the relationships between nodes and their universality. For example, the same graph structure can represent social networks or atom networks with molecules. Then graph neural networks can effectively characterize the structural semantics where the message passing. Jason is one of the most famous gene models with adapted convolutional neural network to graph domain and can be seen as a low-pass filter from the spectral view. Classes sampled a fixed number of neighbors to improve efficiency and designed diverse aggregation methods to improve flexibility. CAT introduced attention mechanism to capture the different importance of neighbors. Knowledge distillation was originally proposed for model compression, where a lightweight student model is trained to mimic the software predictions of a pre-trained teacher model. The student can benefit from the knowledge of the teacher, and so it is more computationally efficient without losing math prediction performance. Besides the motivation of compressing models, recent studies found that a student can even outperform its teacher if they are parameterized identically. In other words, a model can achieve better prediction performance if it learns from a pre-trained teacher model with the same architecture rather than ground truth labels. Recently, there have been several works applying knowledge distillation to improve the efficiency or effectiveness of genes. From the perspective of efficiency, knowledge distillation can be used to compress a deep gene model into a shallow one. For faster inference, from the perspective of effectiveness, knowledge distribution can extract the knowledge of a given teacher and inject it into a well-designed student to utilize more previous knowledge and thus predict more precisely. Besides the choice of teacher and student, the distillation process which determines how the software predictions and the student teacher model and the student model are matched in the loss function is also vital to the prediction performance of a distilled student. On downstream tasks, for example, a global temperature hyperparameter, which softens the prediction of both teacher and student models, is widely adopted in knowledge distillation to facilitate the knowledge transfer. However, to the best of our knowledge, existing knowledge distillation methods applied on genes or employed predefined distillation process, such as with only hyperparameter but without any lineable parameter. In other words, the distillation process are designed heuristically or empirically without any supervision from the performance of distilled students, which isolates distillation from evaluation and thus will lead to suboptimal results. To overcome the isolation problem between distillation and evaluation, instead of introducing the global temperature as a hyperparameter, we propose to learn node-specific temperatures supervised by the performance of distilled gene student. Then we propose a novel algorithm based on an iterative process to train node-specific temperature for better distillation performance. Experimental results on 5 benchmark datasets demonstrates the effectiveness of our proposed framework. This is an overview of our proposed framework. We aim to propose a general knowledge distillation framework that can be applied on any pre-trained gene model to further improve their performance. We focus on the distillation process rather than the choice of student and teacher models, and thus we simply let a student model with typical student model have the same neural architecture with its teacher as suggested in previous works. Compared with the typical knowledge distillation framework, we proposed to learn node-specific temperature, while others use a fixed global temperature hyperparameter. Specifically, we parameterize each node's temperature by a function of its neighbors' encoding and predictions. Then we let the temperature supervised by downstream tasks compared to the traditional knowledge distillation method. We divided the training set into 2 parts, one for distillation loss and other for temperature training, named the evaluation loss. Unfortunately, the partial derivative of a distilled student's performance with respect to node temperature doesn't exist, which makes it non-trivial to learn the parameters in temperature parameterization. Therefore, we design a novel iterative learning process, such as meta-learning, which alternatively perform preparation, distillation, and learning step for parameter training. Originally, evaluation loss is independent of the temperature parameter, but by updating the parameter of the student model one step first, evaluation loss is related to the temperature parameter. In the preparation step, we will compute the temperature for each node with current parameters and set up a knowledge distillation loss based on the node-specific temperatures. And then in the distillation step, the parameters of gene student will be updated by the distillation loss. Then in the linear step, the parameters in temperature modeling will be updated towards higher classification accuracy of distilled gene student. For faster distillation, we introduced a simplified version of LTD named LTD Plus. By heuristically updating the specific temperatures, in order to calculate an appropriate temperature for each node, we need to use the features considered in the temperature parameterization of LTD. This formulation is inspired by the learned temperature of LTD, where nodes with smaller losses and larger neighbor entropy will have higher temperature. In our experiment, we employ 5 benchmark datasets widely used in previous work, and we use GCNGT grasses, SGC, APPNP as teacher and student models to validate our motivation of linear node-specific distillation temperature, we tested several frameworks based on different gene teacher and student models, such as FT, which means a fixed temperature, and LTD without linear steps, and LTD, which is our proposed method, and LTD plus is a scalable version of LTD. Here is the experimental results. From the table, we can see that gene students distilled by our proposed LTD can achieve constant improvements over all 5 gene models on the 5 data sets compared with the pre-trained gene teacher. And this column with the gene teacher, the student distilled by our LTD have a constant improvement compared with the student distilled by a fixed temperature hyperparameter. Our distilled student has relative improvements in prediction accuracy. This observation verifies our motivation of learning node-specific temperatures and demonstrates the effectiveness of our method. We also compare our LTD with two SOTA distillation framework for genes. This figure shows the average accuracy of the 3 frameworks. We can see that LTD constantly performs the best for all 5 genes. These methods all employed CPF, RDD, free KD, and graph AKD all employed predefined distillation process, while LTD can learn a distillation objective towards better generalization ability. Meanwhile, LTD Plus is also very competitive. In order to verify the efficiency of our model, we also compare the running time of a single epoch for different distillation frameworks. In this figure, we can see that LTD Plus and FT are the fastest. LTD and CPF are comparable, and RDD is the slowest. To conclude, LTD offers the best prediction performance, while LTD Plus is the cost-effective choice for large graphs. Okay, this is our conclusion. First, we propose a novel knowledge distillation framework, which can be applied on any pre-trained gene models. And we propose to learn the specific distillation temperatures, and we design a novel iterative learning process for model distilling. And we conducted lots of experiments to demonstrate the effectiveness of our framework. Oh, that's all. Thank you.